Section: Introduction. In this section, we introduce our work on how physical agents, like humans, respond to external stimuli with motor actions that are closely linked to the source of those stimuli. For instance, when surfing, the lower body, particularly the feet and ankles, plays a crucial role in maintaining balance against the waves. We note that humans have feedback loops in their spinal cord that help manage these responses effectively. This localized corrective action is vital for smooth movement, a principle that also applies to robots. However, current robot learning systems often fail to utilize the spatial relationships between their sensors and actuators, relying instead on architectures designed for tasks like language processing or image recognition. Our focus is on transformer policies, which are effective in managing long sequences of data. The transformer architecture was initially created for natural language processing tasks, where the input and output sequences can be rearranged. We propose the body transformer, or BOT, which enhances the attention mechanism of transformers by considering the spatial arrangement of sensors and actuators on a robot. We model the robot's body as a graph, with sensors and actuators as nodes, and apply a sparse mask in the attention layers to limit each node's focus to its immediate neighbors. Stacking multiple BOT layers allows for information pooling across the graph without losing the architecture's representational strength. Our contributions include the introduction of the BOT architecture, which integrates a new masking technique that reflects the robot's physical structure. We demonstrate how this architecture improves performance in imitation learning, leading to better stability and generalization, as well as enhanced scaling capabilities. Additionally, we show that BOT enhances online reinforcement learning, outperforming traditional multilayer perceptron and standard transformer models. We also analyze the computational benefits of BOT, revealing that our reformulation of the attention operation can significantly reduce runtime and computational load. In the related work section, we discuss how transformers, initially designed for natural language processing, have been successfully adapted for various fields, including robotics. Previous studies have applied transformers to represent robot policies, highlighting their advantages in managing variable context lengths and long sequences. However, these applications often do not consider the unique structure of robots. We also explore graph neural networks, GNNs, which process data in graph form. While early GNNs used explicit message passing methods, newer versions primarily rely on attention-based techniques. The standard transformer can handle fully connected graphs, but achieving top performance in graph tasks often requires modifications to the original architecture. Some recent works have implemented masked attention layers, where nodes only focus on their neighbors, which we adapt for policy learning in our approach. Finally, we emphasize the importance of utilizing body structure in policy learning. Previous research has explored GNNs for multitask reinforcement learning across different robot designs, but these methods have mostly been tested in simulations. Our work demonstrates that by incorporating bottlenecks in the attention mask, we can fully leverage the robot's physical structure, leading to improved performance in single-agent tasks and better scalability. In the background section, we explain the attention mechanisms in transformers, which are central to our work. The self-attention mechanism assigns weights to elements in a sequence based on scores derived from pairs of keys and queries from the same sequence. This allows the model to identify relevant elements effectively. The output of the self-attention process is calculated through a specific matrix operation involving query, key, and value matrices, which are learnable projections of the sequence elements. Higher correspondence between embedding pairs results in higher scores, leading to greater influence of the corresponding value vectors in the output. Section Summary. In this section, we introduce the body transformer (BOT) architecture, which enhances traditional transformer models by incorporating the spatial relationships between sensors and actuators in robotic systems, leading to improved performance in imitation learning and reinforcement learning. We also discuss how BOT's novel masking technique optimizes attention mechanisms, resulting in significant computational efficiency and better scaling properties compared to existing architectures. Section: Transformer-based GNNs. In this section, we model the agent's embodiment as a graph, where the nodes represent sensors and actuators, and the edges illustrate the body structure. While message-passing graph neural networks, GNNs, fit this model, they often face issues like oversmoothing and oversquashing, which hinder long-range interactions and limit network depth. Recently, self-attention has emerged as a viable alternative. Unlike standard self-attention, which treats the graph as fully connected, the Graphformer introduces node-edge information through graph-based positional encodings and modifies the scaled dot product using a learnable matrix that adapts based on graph features, such as the shortest path or adjacency matrix, allowing for flexible graph structure encoding. We can also modify the attention mechanism using a binary mask, which effectively controls which node pairs contribute to the attention computation. In our approach, we utilize the embodiment structure to enhance the inductive bias in transformers while maintaining their representation capabilities. We introduce the body transformer, BOT, which employs masked attention, allowing each node to focus only on itself and its immediate neighbors. This design enables information to flow according to the graph structure, with earlier layers processing local information and later layers aggregating more global insights. We outline the components of the BOT architecture. 1. A tokenizer that converts sensory inputs into node embeddings. 2. A transformer encoder that processes these embeddings and produces output features of the same size. And 3. A detokenizer that translates these features into actions or values for reinforcement learning. In the tokenizer, we map the observation vector to a graph of local observations, assigning global data to the root and local data to limb nodes. A linear layer then transforms the local state vector into an embedding vector. Each node state undergoes a unique linear projection, resulting in a sequence of embeddings corresponding to the number of nodes. For the BOT encoder, we utilize a standard transformer encoder with multiple layers and present two variations: BOT hard, which applies a binary mask reflecting the graph structure, allowing nodes to attend to themselves and their neighbors, and BOT mix, which alternates between masked and unmasked attention layers. This approach is effective in our experiments, particularly with the first layer being masked, and our mask allows nodes to always attend to themselves. Finally, the detokenizer takes the output features from the transformer encoder and projects them into actions for the limbs, with separate learnable layers for each node. When BOT functions as a critic in reinforcement learning, it outputs values instead of actions, which are averaged across body parts. Section Summary. In this section, we propose the body transformer, BOT, which utilizes a masked attention mechanism to enhance robot learning by allowing nodes to attend only to themselves and their direct neighbors, thereby leveraging the embodiment structure for improved information flow. We detail the architecture components, including a tokenizer for sensory inputs, a transformer encoder with structured attention, and a detokenizer for action outputs, all designed to maintain computational efficiency while effectively encoding graph structures. Section: Experiments. In this section, we assess the performance of BOT across in both imitation learning and reinforcement learning settings. We maintain the same structure as shown in the teaser figure, only substituting the BOT encoder with various baseline architectures to isolate the encoder's impact. Specifically, we examine several baselines. A multilayer perceptron that uses all embedding vectors as input. A standard unmasked transformer encoder. BOT hard, which employs only masked self-attention layers. And BOT mix, which alternates between masked and unmasked self-attention layers. All models compared have a similar number of trainable parameters. Through these experiments, we aim to answer several questions. Does masked attention enhance imitation learning performance and generalization? Does BOT show improved scaling compared to a standard transformer? Is BOT suitable for reinforcement learning, and what design choices can optimize its performance? Can BOT policies be applied to real-world robotics tasks? What are the computational benefits of using masked attention? For the imitation learning experiments, we evaluate the BOT architecture in a body tracking task using the mocap-ACT dataset, which includes over 5 million transitions across 835 tracking clips. We train a deterministic behavioral cloning policy for each architecture and assess mean returns normalized by clip length, as well as the normalized length of episodes, which end when tracking error exceeds a threshold. We conduct evaluations on both training and unseen validation clips. Our results, shown in the corresponding table, indicate that BOT consistently outperforms the MLP and transformer baselines, with the performance gap widening on unseen clips, highlighting the generalization benefits of the embodiment-aware inductive bias. We also compare our results with a tailored multi-clip policy from the MoCap Act dataset. Although this multi-clip policy performs competitively with the vanilla transformer baseline, it is significantly outperformed by our architecture, even under conditions that favor the baseline, such as its more flexible stochastic policy and larger training set. Additionally, we observe that BOT hard demonstrates strong scaling capabilities, with performance improving alongside the number of trainable parameters, suggesting it does not overfit due to the embodiment bias. In the reinforcement learning experiments, we evaluate BOT and the baselines using proximal policy optimization on 4 robotic control tasks in Isaac Gym: humanoid mod, humanoid board, humanoid hill, and A1 walk. We enhance the classical humanoid environment by increasing the sensory information and including contact forces. Each task varies in complexity, from running on flat ground to balancing on a board or navigating hilly terrain. Our findings show that BOT mix consistently outperforms both the MLP and vanilla transformer baselines in terms of sample efficiency and overall performance, demonstrating the effectiveness of incorporating body-induced biases into the policy network. While BOT hard excels in simpler tasks like A1 walk and humanoid mod, it struggles in more complex tasks like humanoid board and humanoid hill due to its constraints on information flow. In these challenging scenarios, BOT mix effectively balances information sharing and global pooling, facilitating better exploration. Conversely, in environments with more regular state changes, such as A1 walk and humanoid mod, BOT hard's strong body-induced bias helps streamline learning. Section Summary. In this section, we evaluate the performance of the BOT architecture against various baseline models in both imitation learning and reinforcement learning tasks, demonstrating that BOT consistently outperforms these baselines, particularly in generalization and sample efficiency. Our findings indicate that the integration of body-induced biases enhances performance, with BOT mix providing a balance for complex tasks while BOT hard excels in simpler environments. Section: Real-world experiments. In this section, we explore real-world experiments. We find that the Isaac Gym simulated locomotion environments are effective for transferring reinforcement learning policies to real-world applications without needing adjustments. To test our architecture suitability for real-time use, we deploy one of the trained BOT policies on a real Unitree A1 robot, modifying the necessary codebases. This is illustrated in the supplementary video, which shows that our architecture can be effectively used in real-world scenarios. We also note that we chose not to use teacher-student training or memory mechanisms, which are often employed in locomotion studies to create more natural movements. Next, we analyze the computational aspects. The connections between a physical agent's body parts are often sparse, and so are the pre-computable masks for embodiment graphs in BOT. This sparsity allows masked attention mechanisms to reduce computational costs by ignoring unnecessary calculations for masked matrix elements. While popular deep learning libraries like PyTorch have optimized routines for matrix multiplication and attention, they do not take advantage of the sparsity in masked attention due to a lack of relevant use cases. To ensure a fair computational comparison, we re-implement the scaled dot product for biased attention using CPU-based NumPy, testing it on a single sample and attention head, with the potential for further parallelization on GPS. Our custom implementation includes 2 key changes. We compute the dot product only for unmasked elements, which reduces the number of floating point operations, and we use only unmasked values for the softmax calculation, further decreasing operations. We measure the average runtime of our attention mechanism implementation across 10,000 sets of randomly generated inputs. The generated masks have a diagonal of 1s and a sparsity level similar to that used in our mocap-ACT experiments. Our results, presented in the computational analysis figure, show speed-ups of up to 206% for 128 nodes, which is relevant for humanoid models with dexterous hands. Overall, our findings indicate that the body-induced bias in our bot architecture not only improves the performance of physical agents but also benefits from the inherent sparsity of the masks. With proper parallelization, this method could significantly shorten the training time for learning algorithms, as detailed in the supplementary materials.